So you remember in the previous video, we defined what we mean by a function space. By analogy to a vector space, we define what we mean by orthogonalization, orthogonality of functions, and so on. So now we're going to use those to do Gram-Schmidt orthogonalization. We'll take a set of linearly independent functions over an interval, and we will do Gram-Schmidt, the normal procedure, the normal steps, but now with our new definitions of inner products as well as norms, to do the Gram-Schmidt orthogonalization to get an orthonormal set of functions as a result. So in the first example, we're just going to take a set of polynomial functions, which are just integer powers of x. So u sub 0 will be x to the 0, which of course is just 1. U sub 1 will be x to the 1, which of course is just x. And then u2 will be x squared, u3 will be x cubed, and so forth, continuing on to infinity. And the interval that we're going to consider is -1 to 1. So this is our a to b. X goes from a to b, -1 to 1. And what we want to do is take these functions, which are linearly independent. You could check the Wronskian to confirm that this is the case. And we want to do Gram-Schmidt orthogonalization on them to produce a set of orthogonal as well as normalized functions. So in this case, I am going to give us a weight function. It's going to be 2n plus 1 over 2, where n, of course, is just this integer power on the x. It's just a constant depending on the value of n. So if you look back in chapter 1 and you look at the steps in Gram-Schmidt, the first step is to pick one of the vectors and now one of the functions. We'll pick the first one, u0, and we want to normalize it. So we take the function itself, which in this case is just 1. We determine its norm, so the norm of u0, and then divide by that to normalize it. Now in this case, n is equal to 0 because we're dealing with u0. And so we have the norm of u0 is the integral from -1 to 1 of w, the weight function, 2n plus 1 over 2, again n being 0, times u0 of x, which is 1, squared. You do that integral, and then you take the square root. And so you end up getting 1. If you'd like, you could pause and check these integration steps. I want to keep the discussion kind of high level and focus on the steps in the Gram-Schmidt and not get bogged down too much into these integrals. But they're correct, and you can check them to be sure that they are. So in any case, the norm of u0 is 1. So we simply divide u0 by its norm, which is 1 over 1, which of course is 1. So that gives us u0 tilde. So we've just taken our first function. We haven't done anything with it other than to normalize it, divide by its norm, so it has quote-unquote length 1. So then the next step is to take u1, which is x, and we're going to change it in a way that makes it orthogonal to u0 tilde, and then we'll normalize it as we did before. Now in order to do that, we're going to need this inner product. So the inner product of u1 with u0 tilde. So if you remember how this works, you take the original function and you subtract off an inner product times the previous function. And that inner product in this case is the u1 with u0 tilde. So if you do that, here's the u1, here's the u0 tilde, which is just 1. Of course, include the weight function where n is equal to 0. You integrate that, apply the limits of integration, and you get 0. So what that means is that u1 is already orthogonal to u0 tilde. So I don't have to do anything to make it orthogonal. They're already orthogonal. So all I have to do with u1 is then normalize it as we did with u0. So I evaluate the norm of u1, which turns out to be 1, divide by that norm, so I get u1 tilde is equal to x. So far it doesn't look like anything interesting is happening, but what we've done is confirm that u1 is indeed orthogonal to u0, which we didn't know ahead of time, and we've normalized both, which ends up dividing by 1, but nevertheless we know that they're normalized. Now what's happening here is we have even functions and we have odd functions. So let me remind you how that works. So even functions are such that f of minus x is equal to f of x. So that means that if I take a function, I can mirror it around the y-axis and it looks the same. So if I have a polynomial with an even power, like y squared, y to the 4, So it has this property of even functions. On the other hand, odd functions are such that f of minus x is equal to minus f of x. So it gets mirrored around the y-axis as well as around the x-axis. So these are odd powers of x. So x to the 1, x to the 3, x to the 5. So they have this property that they mirror around both axes. Okay, so why do I say that? Well, over this interval from minus 1 to 1, all of the odd functions are orthogonal with all of the even functions. So any inner product of an odd function with an even function is going to be 0. Now if it's odd with odd or even with even, it won't be 0, but odd with even with odd, it will be 0. So for example, for the next function u2, which is x squared, here's the expression that we use to get u2 hat. So we start with u2, the original function. We subtract off a term for each of the previous functions that have already been orthonormalized. They involve an inner product of the new with that one times that one, inner product of the new one with that one times that one. But in this case, whenever I have an even and an odd function, that inner product is going to be 0. Again, over this interval. If I change the interval, that's no longer true. Okay, so this term vanishes, and so I just need the inner product of u2 with u0 tilde. So u2 is x squared, u0 tilde is 1. I incorporate the corresponding w, do the integration, put in the limits of integration, and I get a third. So that's this inner product right here. So now u2 hat will be u2 minus this inner product, which is a third, times the u0 tilde function that we already have. So when I put that together, I have u2 hat, u2 is x squared, this term is gone, minus this inner product, which is 1/3, times u0 tilde, which is just 1. So x squared minus a third. And again, this comes from here, and this comes from here. So that's u2 hat. So u2 hat is a function that's orthogonal to u1 tilde as well as u0 tilde. Then we normalize it. We get the norm of u2 hat. Turns out to be 2/3. Divide by that, and we get 3x squared minus 1 over 2. So you remember that every time you introduce a new vector or now function in the Gram-Schmidt orthogonalization procedure, there's more work to do. There's one more vector, there's one more function that you have to be sure that the new one is mutually orthogonal with. If you're to do the same thing for u3, this is what you would get for u3 tilde. It's 5x cubed minus 3x over 2. Now, these are polynomials, obviously. They started out as polynomials, they stayed polynomials. They're polynomials of the same order. So for example, u3 was x to the 3. It's still a third order polynomial, but it's been changed a little bit. And it's been changed such that all of these functions are mutually orthogonal, so they're a more convenient basis to use for some other purpose. They've also been normalized, and it turns out they have a special name. They're called Legendre polynomials, and they're special because they have this property of orthogonality and being normalized over this interval from minus 1 to 1. So you may have heard of Legendre polynomials, and this is why they're useful, because they have these properties. We denote them by p sub n of x, and they go on for infinity. There's an infinite number of them. We'll come back to Legendre polynomials later in chapter 3, and I'll give you actually a recursion relationship that'll show you how you can get any number of these that you want. So now, of course, the point in doing all this is now I can take any function, any piecewise continuous function, say f of x or u of x or whatever, in this interval from minus 1 to 1, and I can write it as a linear combination of this infinity of orthonormal basis functions that we've just obtained using Gram-Schmidt orthogonalization. So I could write my f of x as a linear combination of all of the Legendre polynomials with the appropriate coefficients, which I can determine. In fact, because the p's are orthonormal, I know that this a sub n hat is simply the inner product of f with each of the pn's. just like in the vector case. So it's the projection of the function on each of the basis functions, and that determines the a(n) hat coefficient. Okay, so that was if we started with a set of polynomials, the x to integer powers. What if we start with a set of sines and cosines, so trig functions? So let's do cosine of nx and sine of mx, where the m's and the n's are integers. So we have cosine of 0x, well that's just 1, then cosine of 1x, cosine 2x, 3x, and so forth. Similarly with the sines, sine of 1x, sine of 2x, sine of 3x, mx. Of course, sine of 0x, well that's just 0. So we have a set of sines and cosines with these varying frequencies, and we want to orthonormalize them. It turns out, and you can check this, that all of the cosine nx's are orthogonal over the interval from 0 to 2 pi with all the other cosines. Likewise, they are orthogonal with all the sines, and all the sines are orthogonal with the other sines. So as a result, all of these are not only linearly independent, they're also orthogonal already. So all we have to do is normalize them in order to have a nice convenient basis to work with using these functions. So for the 1 term, it turns out that to normalize that, you need this factor 1 over root 2 pi. For all the cosine as well as the sine terms, you need this factor 1 over root pi. So if you put that all together, that means that over this interval from 0 to 2 pi, any piecewise continuous function, say f of x, can be written as a linear combination of the constant term, the cosine terms, and the sine terms. So you can see the summation for the cosine, summation for the sines, and we've added these coefficients in a0, an, and bm, those coefficients, into our linear combination. This may look familiar. The a0, an, and bm coefficients then are just inner products, and these are the Fourier coefficients in a Fourier series. So this expression right here is the Fourier series expansion of f of x in terms of a constant cosine nx, sine mx terms. And these coefficients arise because of the inner products, the projections of the f's on each of the functions, as we had in the previous case. So this is a Fourier series, which also should sound familiar. We'll talk again more about Fourier series in a later section in the chapter. But now again, the point being that any function, piecewise continuous function f of x or u of x or whatever, can be expressed as a linear combination using the Fourier series. Okay, so let's make some remarks to close out this section. So we have an infinite set of orthogonal functions, u0 through u infinity. We say that that set is complete if what we've been saying is true. In other words, if I really can take any piecewise continuous function and write it as a linear combination of those. Now in the vector context, we would need a capital N dimensional vector space in order to do that. Now we need an infinite dimensional function space. It's always infinite dimensional in the context of these functions. And so therefore I need an infinity of mutually orthogonal functions in order to span that infinite dimensional space. Now we can extend this beyond the one-dimensional case we've been looking at in X to higher dimensions, X and Y, X, Y, and Z, just by extending the definitions of inner products and norms. So for example, the inner product of two-dimensional functions, say u of xy and v of xy, again, use the same angle bracket notation, well that would just be then the double integral of u times v, integrating over both x and y. So we're integrating over an area instead of just over a domain in x. And then of course the weight function could be a function of both x and y. So we can extend these ideas to any dimension that we would like. We call these functions special functions because they're special in some way, and there's many of them. Legendre polynomials, Fourier series we've seen here. There's a whole book somewhere here. Yeah, so here it is. So Abramowitz and Stegen. So this was written in the early 60s, and it's just page after page of special functions talking about their properties, limits, tables of these values because we didn't have calculators, we didn't have MATLAB and Mathematica at the time. So this used to be the Bible for special functions.